Today we're tackling JNCIA-Junos. 7 questions, 90 minutes, 65% to pass. Let's get right into question 1.
Yeah, let's set the scene. You've got a LAN with 2 switches, a trunk link, and multiple VLANs.
Right.
So broadcasts are properly isolated, but you're still seeing collisions on some ports. Why?
Well, looking at the options, my brain instantly jumps to option B, that VLANs isolate collision domains. It's, a cognitive bias to think of VLAN automatically fixes every physical network issue.
Oh, it's such a common trap.
Oh.
But no, the answer is A. VLANs isolate broadcast domains, but every single switch port is still its own collision domain.
Right, so VLANs are basically soundproof rooms. They stop the loud broadcasts from annoying the whole building.
Exactly.
But the ports themselves are like walkie-talkie channels. If 2 devices talk on the exact same channel at the exact same time, you get a collision.
Spot on. And knowing that physical reality eliminates B and also C, which falsely claims trunk links merge broadcast domains.
They don't.
Right. So how do we actually move messages between these soundproof rooms?
That brings us perfectly to question 2. Devices in the same subnet use switching, but different subnets use routing. What are their actual roles?
Yeah, what do they actually do?
If I'm a new admin, I might be really tempted by option A, this idea that switches forward traffic between subnets and routers filter within a LAN.
I have to politely disagree with that instinct.
Oh, really?
Yeah. In the real world, the actual answer is B. Routers forward traffic between subnets and switches forward frames within a LAN.
Oh, okay. So the switch is like your local office mailroom sorting mail for the people inside the building?
Yes.
And the router is the external post office sending mail out to totally different cities.
Perfect analogy. That eliminates A and D as well.
Yeah.
Because routers don't handle MC learning that is entirely a switch's job. But what happens if that local mailroom gets physically jammed up?
Let's look at question 3. You've got intermittent connectivity, retransmissions, and collisions on a shared segment.
Now, a lot of folks jump straight to option A. Here, they suspect a VLAN tagging mismatch because we love to overcomplicate layer 2 physical limits when we troubleshoot.
Right, but the answer is actually be a half-duplex configuration. It's exactly like a one-lane bridge.
Exactly.
Cars are absolutely going to crash into each other if they don't take turns crossing.
Spot on. Half duplex means a port literally cannot send and receive simultaneously.
Makes sense.
That knocks out the VLAN trap in A in option C, because subnet masks affect layer 3 routing, not Ethernet collisions. So how do devices actually find each other to cross that bridge in the first place?
Question 4 covers exactly that. A host sends a broadcast request and gets a unicast reply to find a mask address.
Okay.
Now, my brain immediately screams option A, DNS, because that's how we navigate the web, right?
Not quite. DNS maps host names to IPs. What we're actually looking at is BARP, the Address Resolution Protocol.
Oh, right. So it's like yelling, who has this IP address in a crowded room? That's the broadcast.
Yes, and then the specific target whispers their MC address directly back to you, the unicast.
That completely knocks out A and DHCP and option C, which just hands out IP configurations.
Right. So if a host needs to reach someone, how does it know whether to yell locally in the room or just send it to the router?
Which brings us to question 5. With a 255.255.255.192 subnet mask, how does a host know if a destination IP is local?
The massive trap here is option D, checking the default gateway first.
Oh, because you'd think the gateway is the boss.
Exactly, but the host doesn't go there right away.
Right. The real answer is B. You apply the subnet mask to both IPs and compare the network portions. It's basically like checking the area code before dialing to see if it's a local call.
Well, I love that. Checking the area code, that eliminates D and A because you wouldn't check MC addresses before knowing if the IP is even local.
Makes sense.
But, since we're physically running out of those older IP addresses, the industry is shifting.
Yes, it is. Question 6 asks for 2 differences between IPv4 and IPv6.
I see people fall for option B all the time here, assuming IPv4 has native IPsec.
Oh.
That was basically an optional bolt-on later.
Yeah, so the correct 2 are A and C. IPv6 uses 128-bit addressing, and since the pool is just so massive, it totally eliminates the need for NAT. Everyone gets a globally unique address.
Exactly. Which eliminates B, and the notation confusion trap in DIPv6 uses hexadecimal notation, not dotted decimal.
Right.
Regardless of the IP version, though, data always needs delivery rules.
Which brings us to our final scenario, question 7. We need 2 protocols, one for guaranteed delivery, one for pure speed. I'm going to argue for ICMP and option C.
Well, ICMP is really just for diagnostics, like your basic pings.
That's
The
true.
actual answers here are A and B, TCP and UDP.
Oh, got it. So TCP is like certified mail. It's guaranteed, tracked, and ordered.
Yep.
And UDP is like throwing postcards out a moving window. It's incredibly fast, minimal overhead, but who knows if they all actually arrive.
That's exactly it. That easily eliminates C and E, since BGP is a routing protocol, not a transport protocol.
Incredible. That wraps up the questions. So today you mastered collision domains and broadcast domains, the function of routers and switches, and the quirks of Ethernet networks.
We also covered Layer 2 addressing, including address resolution, up to Layer 3/IP addressing, including subnet masks.
Finally, we compared IPv4/IPv6 and connection-oriented versus connectionless protocols.
So to leave you with a thought, as networks become entirely virtualized, will the physical concepts of collision domains eventually disappear entirely?